Okay, so welcome to this last lecture on this course on control engineering, and to continue on what we had learned in state space techniques. So we started off by writing down state space equations, then we analyzed stability by looking at linearization of a nonlinear system. Then we looked at stability in terms of the eigenvalues of the matrix A. So we'll go a little further and see what else can we do with the state space analysis. So we'll keep the analysis to a very minimal, right? So I will not do proofs of what I'm going to talk about. I just give you a very general idea for a very maybe just small 2 by 2 systems. Okay, so the first thing which we will learn is the notion of controllability. So we start with a general state space system. X dot is Ax plus Bu and Y is Cx plus Du, where as usual x is a n dimensional state vector, A is the system matrix which is of dimension n cross n, U is a control input, could be an m dimensional input, it could also just be a one dimensional input or just a scalar input. C is a p cross n matrix given that Y is a set of n m outputs. I'll just write it down here. So Y is the output vector and could be an a p vector, and the input is m vector. Okay, so what else can we do now? So just given a system x dot equal to Ax, I know how to find out stability. I also know how to go from the state space representation to the transfer function. This we had learned in the earlier lecture. So I'll just write down the formula for you again. G of S is C Si minus A inverse B plus D. Okay. Okay, so this has all been good so far. Now, a very important notion. So far when we were doing the entire transfer function based analysis of designing compensators in via root locus, via the frequency domain, Bode plots, steady state errors and so on, we never asked ourselves, is the system controllable? Right? We just say, okay, so given this system of given a certain transfer function, as long as it is stable or stabilizable, as long as I could pull the root locus to the left of plane and things like that. I even knew in the Nyquist plot that I could start with a open loop unstable system, end up with a closed loop stable system. I never asked, is it controllable, before I even start controlling. Now, even before I answer is it controllable or not, first we need to formalize the notion of controllability. Okay, so but the definition says that a system is controllable at some time t0 if it is possible by means of any unconstrained control vector u to transfer the system from any initial state to any other state in a finite interval of time. Okay, let us say just if I just were to draw it graphically, let us say I have a 2-dimensional state space x1 and x2 both in T. Now I say given any initial state here, okay, can I transfer to any other state? It should be in the entire R2, entire of this 2-dimensional space. Can I go, for example, from here till here by application of some control, say U1 in some finite time T1? And that is true for all points from here till here, here, here and so on, right. So is it possible by means of any unconstrained control? I don't have a limit on the amount of control effort I put it. I say, well, can I at least control? Maybe the effort is really large. Unconstrained control vector to transfer from any initial state to any other final state in a finite interval of time. Now this finite interval of time is important. Now there could be systems which are just partially controllable. Again, I will not go to the details of this, but I will just tell. So if I have, say, systems with, say, some n states, so which means x is a vector x1 till xn, and I say that the first n over 2 states are controllable and the remaining n over 2 states are uncontrollable. Okay. So these are controllable states, these are uncontrollable states. Now, what can I do with these systems is I just ask a question is are these systems stabilizable? It is a little weaker notion of controllability. So, I can do anything good with the system as long as the uncontrollable modes are stable. Right? If these are stable, then I can do something with these control modes here. So, for partially controllable systems, partially controllable here means I can control only half the states. If the uncontrollable modes are stable, these are the uncontrollable modes, and the other modes are controllable, then the system is stabilizable. Okay, so what could be a very vague example of this? So, let us say I am in a small classroom and I want to control the classroom. Control essentially would mean here I just want to not make not the students should not have any crosstalk, they should not make any noise, for example, like in a high school. So, if nobody is there, there is no control input, there is no teacher in the class, there is no control input. So, the entire class is in a mess, everybody is shouting, talking, throwing paper balls and stuff like that. Now, say I enter the classroom, say the classroom has 10 people, and it is more or less possible that I could control the 10 guys. I could just maybe warn them by whatever means I could control them. I could threaten them, I could say I will give you 2 marks less, or I will give you a chocolate or things like that, and I could control. Now, say if the size of the classroom is say 20, I could possibly still manage. If it is say 100, then there could be 2 people who could control the classroom, right. If there are say 500, and it is very likely that only 2 people may not be able to control the classroom. So, I can split that classroom into mischievous guys and good guys, and I assume that the mischievous guys that the entire all these guys are good guys and they are controllable. So, if I say the amount of mischievous guys is 100 and the good guys are say 400, that they are just quiet by themselves. Now, I ask my question is, and I actually do not have control over the 400, say the first 100 are sitting in the first couple of rows, and then the 400 guys are really far, that even if I shout or yell at them, they will not be able to listen, but they are all quiet guys, they will naturally be quiet, right. So, here it says that the system is partially controllable, I only have access to the first 100 guys. So, this entire classroom is stabilizable, I would say, or it can be made quiet only if the other 400 guys whom I do not have any control of are quiet by themselves. I could control the first 100 guys, right. So, this is a very, and I am just thinking of an example, and the best non-engineering example I could come up was this one. So, these are partially controllable systems where I say I could do something, I can make the class quieter only if the guys whom I do not have access to are quiet by themselves. Okay, now how to test controllability? So, what am I given? I am given this equation x dot is ax plus bu, and I say can I start from x and initial condition x naught, if I may call it. So, I will just let me denote this as x naught, and I will go to some say state x at t1, some finite time t, and with some unconstrained control. So, can I do something with this differential equation? So, the solution to this differential equation would look like this. So, I have a e power at. Okay, let us not really worry about how the exponential of a matrix looks like, that is a very detailed topic by itself, but just assume that if I, okay, this is a very crude and not a very smart way of looking at it, but if I have say a scalar differential equation x dot equal to small a and x, where x is just a one dimensional vector, it is in R, then I say that the solution is x of t is e power a t x naught. Okay. Now, similarly, if this is a vector, x is in Rn, as in our case, A is n cross n matrix, then this exponential would be replaced by e power at. On the left hand side, I will have a vector of dimension n, and my initial condition will also be a vector of dimension n, right. Okay, so I should not really write this a multiplied by t, just write it a So, not a of t, but I should write it simply a multiplied by t. Okay. So, how to compute this is not really important, but this is also called the state transition matrix. So, it means that given a certain x naught, how will my system, the system is defined by a, will take this initial condition over time to some other xt. Okay, just the evolution of an initial condition. So, if I have the input, I will have something like this. So, what is unknown in this? Okay. So, if I just a little write down this, say I have, let me for example for simply assume that x of 0 is some number and say x of t, I want to go to the origin, right, from any initial condition. So, this would look like minus x, sorry. So, on the left hand side I will have 0, I get these guys here. So, this would be x naught e power minus a t would be integral of all this entire thing, e power a t minus tau b u tau d tau. So, essentially here I am the answer or the problem here is to, okay, what are known to me? The initial condition is known to me, the final condition is the origin, a is known to me, b is known to me, and this is looks like an equation, right. So, given a, b, the initial condition, can I say that I can go from an initial condition any non-zero to a 0 final condition. So, the only unknown is this one, u of t, right. So, does there exist a solution u of t such that this equation is solvable? So, that is the entire controllability problem. Again, I will not go into the details of computing how the solution goes, but I will just directly introduce to you to the way of checking this one. Okay. So, the system is completely controllable if and only if the rank of this matrix n cross n times n cross m, that's this b is, if you look at here, b is an n cross m matrix, and I keep on doing this, that this matrix should be of rank n, right, and I say that the system is then completely controllable, this one. Okay. So, let's do something else now, right. So, to really understand these concepts in a different way. Okay, I will use this after a very long time. Okay, so let me start with a simple looking example. Let me say I have a circuit which looks like this. I have R, this is R1, C1, R2, C2, and input, I call it V, say some U, say it's a current source. Okay. So, this is how it looks like. Okay. So, first is, what are the states? Well, the states, if I could call the voltages across these as states, so I will call this as the voltage across the capacitor C1 as V1 and as V1, and then the voltage across the capacitor C2 as V2. So, I can write down equations. Okay, what is the first? So, this is a current source, the total currents add up. I can say that R1 C1 dV1 by dt is minus of V1 plus U. Okay. Similarly, for dV2 by dt, so that is or say dV2 by dt is, okay, I just get this in the denominator, minus 1 over R2 C2 V2 plus U over R2 C2. Okay. So, I just write down these equations now, say in the state space form, V1 dot V2 dot is minus 1 over R1 C1 0 0 minus 1 over R2 C2 with V1 V2 plus what I now have is 1 over R1 C1 1 over R2 C2 times U. Okay. So, what does control mean in this case? Okay. So, if I look at this in terms of solving my differential equation, for example, given a input current here, can I starting from any initial condition, can I get say C1 to be at 5 volts and C2 to be at say 7.5 volts, or either ways it could be 6 here, it could be a 9 here and so on, all possible combinations. Can I stabilize them to some arbitrary voltages? Okay. So, how will my solution look like? Solution, if I say, okay, so let me just call this in the standard notation, this is x dot of t. Okay. So, x of t here would be e power minus 1 over R1 C1 x1 of 0, x1 is V1, right. So, I am just calling this V's to be x, and e power minus 1 over R2 C2 x2 of 0, okay, plus 0 to t, again all the other terms, right, which will have the b u t minus tau d tau. So, this will be e power minus t minus tau over R1 C1 and this entire guy divided by R1 C1, and it is e power minus t minus tau over R2 C2 with the entire guy divided by R2 C2, and I have u tau d tau. Okay. Now, let me take a special case where the time constants are the same, where 1 over R1 C1 is 1 over R2 C2. Okay. Okay. So, what happens in that case is my x of t would be, okay, e power minus t, again I have the two initial states, right, x1 naught x2 naught plus integral. So, if I go back to the previous one, here, right. So, this all these are the same, R1 C1 equal to R2 C2, and let me even call this as 1, right, for simplicity, and therefore, say all these will be 1. So, x1, if this is, so this vector essentially is x1 and x2. So, x1 is e power minus e power minus what is it? So, from the first, okay, what the hell is happening? Okay, sorry, I just missed a t here, right. So, this one, this, and this is, so this is like the e power a t x naught. Okay, sorry, I just missed the t here. So, if I write down these two equations separately, or I just maybe club them into one. So, how will the overall solution look like? So, this is integral. So, all the parameters are set to 1, 0 to t e power minus t minus tau u tau, all this multiplied by 1 and a 1 and a d tau, because they are the same, right. So, here, so this e power minus t minus tau, this is 1, this is 1, this is 1, this is 1. So, both are the same numbers essentially, both are the same numbers multiplied by u tau d tau. Okay. So, okay, look at this, and I'll ask starting from, so this is our question, right, starting from x1 0, x2 0, what are the states final states I can reach. Final states which one can reach. Okay, or starting from here, what all points I can control my system to. Okay, so look at this thing, right? So this entire thing here for a particular input would be just a constant, right? So my x of t, and let me also assume for simplicity that x1 of 0 is x2 of 0 is the origin. Doesn't really matter, right? So in a linear system, I am here, I am here. If I can go from here to here, it also would mean I can come back here. It's a simple proof, but just assume that we know this, or we will try to believe this. Okay. So my solution, all possible places where I can go starting from this is my initial condition, x1 naught, x2 naught. So x of t is some function, let me call this some alpha t, alpha t 1 1. Okay, if I just write down the vector thing, this would be x1 of t, x2 of t is, so both are at the same values, alpha t, alpha t. And I started my problem by posing the question, can I get capacitor 1 to 5 volts, capacitor 2 to 7.5 volts? Well, the answer in this case is that I cannot. If this is, if C1, if V1 goes to 5, V2 should also go to 5. Now this is happening in this special case only, when R1 C1 and R2 C2 both have the same values. For all other values, I can see that the system is controllable. So I could just compute the B matrix, AB, and check for its rank. Okay, this will be some matrix. Okay, B is 1 over R1 C1, 1 over R2 C2, A times B, what is this? A is 1 over R1 C1, 0 0, minus 1 over R2 C2, and I multiply this with B. What is B? This is R1 C1, R2 C2. So this essentially is, so I will have minus 1 over R1 C1 square, and here I will have 1 over, with a minus sign, R2 C2 square, right. So the rank of this should be 2, which means I look at the determinant and it says, okay, minus 1 over R1 C1, 1 over R2 C2 square, this, plus 1 over R1 C1 square, R2 C2, this should not be 0. And then it's full rank. And you see in the special case, when everything becomes 1, it goes to 0. So it loses controllability. So for all other values apart from this one, I can get to a configuration like this, right. I can go, this can go, V1 can go at 5, V2 to 7.5 and so on. But for some particular value of R1 C1, R2 C2, the system is not controllable. Okay, but let's also see what happens when the system is not controllable. What does it mean in terms of transfer functions? Okay, let me instead consider a circuit which looks like this. I have a U, L, I have a R, so this is R, this is R. I measure the output as the voltage here, plus minus Y, this is plus minus Vc, the current here is IL, and it's quite natural to choose IL and Vc as the states of the system. Okay, so let's first write down the state equations for this. Okay, so I'll how do you start with? So you have, so let me call this as x1, I'll call this as x2, I write down the equations L x1 dot plus R x1, this is x1 is IL from here. So, this will be x2 plus R C x2 dot. Okay, so from here with the plus here, and similarly x2 dot is u minus x1, and the final equation y is u minus x1 times r, which results in the state space equation, which is like this: x1 dot x2 dot is minus 2 times r over L. I have 1 over L minus 1 over C, 0. I have x1 x2 plus r over L 1 over C times u, and the output y in terms of Cx plus du is minus r 0 x1 x2 plus r times u. Okay. Now, first is this system controllable? Well, the idea would be to check the rank of B, AB. So, this is usually also referred to as the controllability matrix. So, this C turns out to be in our case as R over L 1 over C. Okay, so, this is the B, and then this is 2 R square over L square plus 1 over LC and minus R over LC. And then you see that the determinant of this C is R square by L square C minus 1 over LC square, or the system is controllable as long as R square is not equal to LC. Okay. So, for all other values the system is controllable. Okay, what does this now mean in terms of transfer functions? So, we know that from the transfer function, the relation between the state space and transfer function. So, given x dot is Ax plus Bu and y equal to Cx plus du, the transfer function g of s is simply C Si minus A inverse B plus D. Okay. Now, let us choose a value, or just choose values of the circuit parameters such that the system is not controllable. So, what it's said here is that R square should not be equal to LC. Okay. Should not be equal to LC. So, let us be notorious and say, well, what happens if R equal to LC, and say everything is equal to 1. You know, so 1 is R, 1 is L, 1 is C. So, the system violates the controllability condition. In that case, my system matrix A becomes minus 2, 1, minus 1, 0, B is 1, 1, C is minus 1, 0, and D is 1. Okay. Now, if I just do the formula, just substitute this here. So, what I get is C, so this entire term C Si minus A inverse B plus D is minus S minus 1 over S square plus 2S plus 1 plus 1. Okay. So, this is also minus of S plus 1. What is on the denominator? This is S plus 1 whole square plus 1. So, this cancels out, and what I am left with is minus 1 over S plus 1 plus 1, and this is what minus 1 plus S plus 1 over S plus 1 is S over S plus 1. Okay. So, what is happening, right? So, how many poles do I have in the system? Well, if I just look at this transfer function after I blindly do all these computations, we will say the system has only one pole, and therefore, we may say it has only one energy storing element. Well, that is not true. The original circuit had two states, this guy IL and VC, and one of those has disappeared now. Okay. So what is happening when the system is uncontrollable is what we see here. Here is a pole zero cancellation. Okay. So whenever there are uncontrollable modes of the system, they get cancelled, or they encounter a pole zero cancellation, and what we see as the remaining transfer function is now the transfer function of only the controllable part of the system. So when we talk about transfer functions, we do all the computations, the simplifications. What we end up with is the transfer function of only the controllable part of the system. There is a proof for that, but we will not do that. So I just would like to show you an evidence that, well, when there is loss of controllability, you see a pole zero cancellation, and what is left is the transfer function of only the controllable part. Okay. So okay, let's go back here. So this is the condition to check. Given a system configuration with a matrix B and A, I can always find out with this rank condition if whether or not the system is controllable. Okay, once I know that the system is controllable, what could I do with that? Right. So while we were doing the root locus analysis, what we were essentially doing is, does the root locus pass through the desired pole locations, the desired dominant pole locations? That was what we were interested in, right? And then we said, well, we design a lead compensator, a lag compensator, and pull or push the root locus such that the root locus of the compensated system passes through the desired closed loop locations. So here also I can ask an appropriate questions, right? So pole placement here means placing the closed loop poles. These are also, what are the poles? The poles were also the eigenvalues of the system matrix A. So can I, by choice of an appropriate controller u equal to minus kx, place all the eigenvalues? So what does this mean? So I have x dot is ax plus bu, and I say u equal to minus k of x is my control law, and if I substitute this here, I have ax minus b kx, or in other words, I have a minus bk times x. So these are the eigenvalues of my original system, the uncontrolled system. Now via the control, my system matrix has changed to this new A tilde, if I can call this. Now can I change, or can I place the poles or the eigenvalues of the closed loop system via this choice? So this shows that, well, something is changing via B and K. Right. So this technique is called the pole placement techniques. So what is the contrast with root locus? Well, in the root locus methods, we were placing only the dominant closed loop poles, whereas in the pole placement design, we can place all the closed loop poles at desired locations. Okay. This is not surprising. Again, this is a good mathematical proof, but we will not do this. We will just learn this with some very small examples. That are necessary and sufficient conditions for arbitrary pole placement. What is arbitrary? If I have n poles here or n eigenvalues, can I place all eigenvalues? Can I shift all the eigenvalues, all the n eigenvalues to desired locations? So this is arbitrary pole placements. So when can I do this? I can do this only if the system is completely controllable, right? So if I just write down some equation, right? So just say I have x1 dot is, say, x plus some k times u. Okay. So what is the eigenvalue of the uncontrolled system? The eigenvalue of the uncontrolled system is at plus 1. Okay. Now, if I say, can I place this at, say, some value minus 2? Well, does there exist a k such that I can place this at minus 2? So how should the my system, which is the control system, look like, the closed loop system? So does there exist x dot, or say, does there exist u equal to, okay, this is also x1 by the way, minus k x1, such that the closed loop system closed loop system is what? X dot is A minus, okay, sorry, let us get this k also out, this looks nicer now. So, x dot equal to x1 plus u. Can I use a controller like this in such a way that the closed loop system is A minus k times x1? The closed loop system looks like this, minus 2 times x1. Okay. Now, what is known to me? I know this A here. So, this A is just 1. So, this is 1 minus k x1. So, this A is just 1. Just write it over here directly. A is 1. So, I just am solving a linear equation now, right. So, 1 minus k is minus 2. So, this means that k is 3. Okay. So, put k equal to 3 here, you just arrive at this one, and this has, starting with a open loop pole which was at plus 1, with YIU equal to kx1, I could place it at minus 2. Right. So, this is essentially the problem of pole placement, right. And what I said, a necessary and sufficient condition for arbitrary pole placement is that the entire system be controllable. So, let us do a little more, some more example. Let us say continue the same one, say x1 dot is x1 plus u, and say I put another state x2 dot is say minus x2. Okay. Now, can I do anything with the poles of x2? Well, the answer is no, because there is no control input influencing the x2. Now, look at the controllability matrix. So, this system has A as 1, 0, 0, minus 1, B is 1 and 0. So, what is B? What is the controllability matrix? C equal to B, AB. So, that is B is 1, 0, and A times B is what? 1 and 0, and this has rank of 1, not equal to 2. This is not full rank, right? This is the n rank, which in this case is 2. So, I can see here that the system loses rank, it is not completely controllable. Therefore, my claim that for arbitrary pole placement, the system should be completely controllable. Well, this is one example of that. This is not a big proof anyways of that. So, just go back to what we said here, that a necessary and sufficient condition for arbitrary pole placement is that the system is completely controllable. Okay. So, let us do one last example here. Okay. So, let us say I have an equation which is like this: x1 dot, x2 dot, this is my system, 0, 1, minus 1, 0, x1, x2 plus 0, 1, u. So, this is essentially the undamped pendulum state space equation. You could have seen this in the previous lectures on state space. Okay. So, my question here is, can I place the poles of the closed loop system via u equal to minus kx at minus 1 and minus 1? Okay. So, how do I go about doing this? So, first I check, is the system controllable? Well, I just again check the rank of B and AB. So, this is my B, this is A. Okay. So, the controllability matrix C is 0, 1. What is AB? This is 1, and this is 1 times 0, this is 0, and this is of rank 2, right. So, well, what I can say here is that I can actually do this, that the system is completely controllable. Therefore, I can place both the poles at minus 1, minus 1. Well, where are the poles of the open loop system? That is just, you look at the solution of the characteristic equation Si minus A equal to 0, and you find that the poles or the eigenvalues are just at plus minus j omega. Okay. Now, can I choose u equal to minus kx, or, well, in this case, since this is a system of 2 variables, I will say k1, k2, x1, x2, such that this holds. Okay, so how will the closed loop system look like? So how will A minus bk look like? This is A is 0 1 minus 1 0 minus, well, what is B? B is 0 1 and k looks like k1 k2, and this is what? This is 0. Okay, this is 0 here, and what will I have here? I will have a 1 here, nothing changes in the first part. Here I have minus 1 minus k1, and here I will have minus k2. Right, so this is my closed loop system matrix, A minus bk. Okay. Now I want the eigenvalues of this system to be at minus 1 minus 1. Okay, so what do I do? Okay, so what is desired is the closed loop system to have eigenvalues of minus 1 minus 1, which means, well, what is then the desired characteristic equation? Well, Si minus A. So I know that, well, since the poles should be placed at minus 1, this should be something like this: S square plus 2S plus 1. Okay. Now what do I have with me? Well, my A minus bk now looks like this. This is 0 1 minus 1 minus k1 minus k2. Okay. Now where are these roots? So what is the characteristic equation from this? I just want to find Si minus A equal to 0. Right. Now this is the characteristic equation. This characteristic equation should just match this one. Okay. This is the desired one. Right. This is what I want. This is the characteristic equation in the unknowns. Unknowns k1 and k2. So this actually is A tilde, right? So just a little, A tilde is actually A minus bk. So if I write down the characteristics equation, so this, after all the computations, the characteristic equation will look something like this: S square plus k2 times S minus 1 plus k1, and this should be equal to the desired one, that is S square plus 2S plus 1, which means that k2 is 2 and minus 1 plus k1 is 1, which essentially means that k1 is minus 2. Okay. So with this controller I can place my closed loop poles to be at the desired location. And how do I check if I can do this or not? It's just by the system being controllable or not. Okay. So this was about controllability. Now if we look at what was this based on, this was essentially based on this equation, this controller u equal to minus kx, which then assumes that I know the entire of x, right? That all x's are measurable, then I can feed back these states. But usually the states are not up for measurement, the states are not available for measurements. What is available instead is the output y. Okay, and this y, okay, let's simply assume for the moment that this d is 0. So what is available for measurement is y equal to c times x. And I can ask myself a question: given this measured values, right, can I get what is x? Well, you can say an answer that then x is c inverse y. This is true when, well, c is invertible, or if y, the dimension of y is the same as the dimension of x. But usually this is not the case. Maybe there are n inputs and p outputs, right? So this is a p vector, this is an n vector, and usually p P is less than N. Then if I were to do this state feedback control law based on these measurements, I should somehow be able to get an estimate of the states from these P measurements, estimate of these N states via P measurements. And that leads to me to define what is observability. Well, again I will not really go into details of anything of this, just to see what is happening. A system is said to be observable at time t0 if with the system starting with xt0, it is possible to determine this state from observations of the output over a finite interval of time from 0 to t, right. Essentially the problem is given x of t, so given set of observations, can I construct x t naught? Well, it turns out that again, so this actually is this measurement here, right. I have measurements y of t from 0 to t, can I construct x t at 0? This turns out that if the rank of this matrix, well, here I assumed that p equal to m, and the number of outputs is equal to the number of inputs, which is generally should not be the case, otherwise it will just be a p n cross n matrix. So nothing, there is no loss of generality here, by the way. So this matrix, which is called the observability matrix, is of rank n. So once this is of rank n, then I can get an estimate of the state via measurements of the output y, and once I know what the states are, I can always design a state feedback control law to place the poles of my closed loop system at the appropriate locations. Okay, so I will not do any of these proofs of why this rank condition is true or why the complete controllability condition is true for placing the poles at arbitrary locations, but just to give a general overview of what is the concept of controllability and observability. Similarly to what happened in the case of controllability, observability also happens when there are pole zero cancellations, which you could again check with the example which we had done. Okay, so that really brings us to the end of this course, and well, I had fun recording these videos. I had fun interacting with you over the discussion forum, sometimes over the hangouts, and I hope it would be useful to you in some form or the other for GATE exams, for your regular university exams, people who are teaching elsewhere, and any kind of feedback is welcome. You could write to us what you would like to improve in the course, what you liked, what you didn't like, what you would like us to elaborate a little more. But overall, I hope it was a good experience for you. Thank you very much, and see you soon.